Hi, Dylan.
Hi, Professor Popovich. How are you?
Peach again. Your dog is barking at you.
Oh, yes. They're mowing our.
They're mowing your grass or something?
Yep, and they are barking.
It gives them something to do, I guess. How are y'all doing, guys? Peachy King, wonderful. Glad to be here. Hey, we got to have one more person in here to beat the morning class. Starting to wonder why I'm doing this twice a day. We doing okay, guys? Yay, nay? I'm getting crickets here, guys.
I'm doing okay.
All right. All right. I'm going to get out of here. We're going to get through solutions today, guys. Ooh-wee. Excitement. And the excitement builds. So I'm just going to go ahead and get started because, to be honest with you, most of you are going to be able to just pick it up from wherever I'm at if they come in here, okay? Basically, we're going to go through some terms and backgrounds. We're going to talk about mass percent. We're going to talk about parts per million, molarity, solution prep, dilution equation, and stoichiometry. It's tons of excitement here, guys. Okay, basically a solution is just a homogeneous mixture. Usually when we think of solutions, we think one of them is going to be a liquid, and generally speaking, the other one's going to be a solid. Now, if we're dealing with the parts of a solution, can you guys see my face?
Yeah.
Okay. Because I can't see my own face, and I'm probably glad of that. If we're talking about the parts of a solution, the solute is the substance that's being dissolved. The solvent is the stuff doing the dissolving. Note, guys, the solvent is usually, but not always, the larger portion. When we're thinking about drinking alcohol, ethanol, which is drinking alcohol, will dissolve in water in all proportions. That is, you can put 5 milliliters of alcohol in 100 milliliters of water, or you could put 5 milliliters of water in 100 milliliters of ethanol. You could put them in there 50-50. They dissolve in all proportions. When we're talking about drinking alcohol, we generally think of the water as being the solvent. Because generally speaking, we're talking about have you heard about proof of alcohol?
Yeah. Which
is basically double the percentage. And you get into something like 151 proof rum, and that's 75% alcohol. Still, because of that, we kind of think of water as being the solvent. Usually the solvent is a larger portion, not always. Now, also you got to remember that the solute and solvent can be a solid, liquid, or gas. If we think about something like brass contains copper and zinc, but it's kind of a flowing movement. Even though it's a metal, it is a solution because they are homogeneously mixed. If you think about air, oxygen and nitrogen, nitrogen is considered the solvent. Oxygen is the solute, along with all the other little ingredients that are in air. So, has anybody ever watched Popeye?
Yeah.
What does Popeye say right before he beats the snot out of Brutus?
Oh, I don't know that one.
You don't know that one? Yeah, he says, I can't takes no more. And then he goes and pops the can of spinach and goes and beats the snot out of Brutus. Well, saturated is that situation where the solution can't, takes no more. Saturated means that the solvent cannot take any more of the solute. Make sense, guys? So a solution is unsaturated if you can add more solute. So my question to you all is, how do you tell if a solution is saturated? You're looking at a solution. There is one thing that tells me immediately that I know that that solution is going to be saturated. Anybody know what that is?
Is it the buildup of something?
Nope, not quite.
No, because like I know with one there was an example. Someone was pouring salt, and he knew that it was saturated when the salt started building up. But
What do you mean building up, Blake?
like you can actually see a pile of it.
There we
yeah.
go. Absolutely. You're absolutely right there. You know it's saturated if you can see a little pile of solid in the bottom, because that means that you cannot put any more in there unless you do something. Blake, can you think of one way that you can get more solutes into a solvent?
Now that you got me, I don't know. Shake it, swirl it, agitate it.
If you agitate it, what happens is you make the water molecules a little more active and they can more effectively surround more of the solute. Can you think of another way that you can agitate the water molecules?
Change the temperature.
Change the temperature. And it depends. If you have something like salt dissolving is an exothermic reaction. So if you add more heat, you're going to force more salt to be dissolved. On the other hand, if you have an endothermic reaction and you heat the water up, chances are you're not going to get as much in there. We also have something that's called a supersaturated solution. Has anybody ever made a mojito or hard candy? And with this group, I'm going to bet that the chances are better that you've made a mojito.
I've definitely made a mojito before.
Cassidy, how did you make it? Did you actually do it from scratch?
I like muddled the mint and sugar together with the lime juice at the bottom, and then
Okay, so you didn't make the simple sugar solution then.
No, I just kind of did everything by hand.
Okay, different recipes. The recipe I have involves using something called a sugar syrup. And basically what you do is you heat up the water, keep on dumping sugar in. And eventually what happens is you make this really oozy, clear solution that is called a sugar solution. It is super saturated. We've got the water molecules in there perfectly aligned so that they've got just as much sugar in there as it possibly can. And actually I've got more sugar in there than I can. And all that it takes is for you to disrupt that by putting like a string in there. If you put a string into that simple sugar syrup, what happens is the sugar goes and collapses right on that string. And that's literally how rock candy is made. Anyway, that's just an example of what supersaturated is. Does anybody know of that fine institution that is just to the north of us? Right beside UF.
Mm-hmm.
Now, Blake, UF is famous for making two different things. Both of them I could curse them for. One of them is love bugs. Somehow love bugs were supposed to eat up all the mosquitoes. We can see how well that worked out. The other thing they came up with this product in the 60s that was designed to prevent their football players from getting cramps.
That's Gatorade.
Gatorade, yes.
Yeah.
Basically Gatorade. What they do is they throw a whole bunch of salt in there. They got to put some sugar in it to make it palatable. And the idea is that when you are using your muscles, you're having signals fired from one nerve to the other, and they get fired by the electrolytes that are in your body, because your body doesn't exactly have copper wire in there. So the whole idea behind this is what they're going to do is when you're sweating, you sweat these electrolytes out. And by putting all these salts in there, you're supposed to be replacing them. They just didn't figure out on one thing. That is, when you drink Gatorade, you generally get rid of it just as fast as you consume it. And the electrolytes go right through you. So in order to be an electrolyte's nothing more than a substance which, when put in water, conducts electricity. So in order to do that, it has to have two properties. It needs to be ionic, and it needs to be soluble in water. So basically, what happens when we dissolve solutes? Through a process called dissociation, what happens is the water molecules surround the individual ions within a crystal, and they separate them from one another. In other words, the water comes in and attaches itself and surrounds each sodium and each chlorine ion and separates them from one another. Now, water is a polar molecule. By that, I mean the electrons are shared within the water molecule, but they're not shared evenly. The electrons like to spend much more time around oxygen than they do around the hydrogen. So the little red balls you see here, they have kind of a negative charge, and the white balls there, they have a positive charge. So what happens is the white balls, the positive charges surround all the negative chlorines, the oxygens surround all the positive sodiums, so that we get these two different ions totally separated from one another. Another illustration of that. So there are reasons for this, and these reasons we are going to get into in chapter 13 or so. But the thing I want you to know from right now is an old chemistry phrase, like dissolves like. Polar solvents, they've kind of got charges around them. So they're going to dissolve polar compounds and ionic compounds, because both of those have charges around them. Non-polar solvents dissolve non-polar compounds. Has anybody ever heard of a substance called napalm?
Yeah.
Yes.
Do you know how to make it?
No.
Oh, the things I teach you. All you got to do is get some gasoline and get some styrofoam cups. Styrofoam is non-polar. It will dissolve in the gasoline. And what it does is it makes this pasty substance that you kind of like can throw at something and it sticks. But you can light it. And when it sticks, it's still burning. I should get paid for giving these little tips. Okay, so far what we've been doing is we've been describing the solutions qualitatively. In the fact that we're talking about what things make up the solution. But we also have to think about them quantitatively, because not only can they vary in what substances are making the solution, but the concentrations within there can vary from one another. So solutions can have varying compositions. So to describe it accurately, you need to know what's in it and how much of it is in it. So when we're talking concentrations, we're talking specifically about the amount of the solute in a given amount of solution. Sorry. There we go. So we're going to talk about some things, some different concentration terms. First one you've already done. You've done mass percents already. We're going to go from there. We're going to also talk about something called parts per million, and from that, parts per billion. We're going to deal with another term called molarity and a last term called molality. We're going to deal with molarity in this course. You won't need molality until you get to the next course. Okay, mass percent. You guys have already done this. We've already done it. It's nothing more than the part divided by the whole times 100. In this case, we're generally, when we're talking about a mass percent, we are generally talking about the solute divided by the solution. So we're going to get the weight of the solute, divide that by the weight of the solution, multiply it by 100%, and we have the mass percent. Again, something you guys have already done. Remember, guys, the solution is equal to the weight of the solute plus the weight of the solvent. What is the mass percent of a solution made by mixing 33.9 grams of ammonium chloride in 100 grams of water? How are we going to do this problem, guys? Remember, it's just part over whole.
Do we add both of them together to get the whole solution?
You have to do that. Absolutely.
And then,
Go ahead.
and then you divide 33.9 by that whole number, by 133.9.
There you go. Absolutely. That's all you have to do for this. The second one, same basic thing. You're going to take 44.7 and divide it by 169.7. The trick behind that is to realize that you have to add both the solvent and the solute. We can have volume percents too. It's the same thing as the mass percent, only instead of weighing out how much of each the solvent we have and the solute, instead of doing that, we measure out, take 10 milliliters of ethanol, put it in there, and measure out 100 milliliters of water, and we're just taking the volumes then. Interesting point. When I was going to school, West Virginia is a very, very interesting state. At 18, I could drink all the hard liquor I wanted, but the only beer that they had was volume to volume. So what we had to do was we had to sneak into Pennsylvania to get the real beer. Okay. If you want to get drunk, would you rather have 6% mass percent alcohol or 6% volume percent? The density of alcohol is 0.79 grams per milliliter. Guys, all you got to do is convert one to the other and compare. The volume is 6 milliliters of ethanol in 100 milliliters of water, or 6 grams of ethanol in 100 grams of water. So basically what I did was I took my 6 milliliters, multiplied it by the density. That means I have 4.74 grams. I do the same thing to water, only that density is 1 gram per milliliter. That means I have 100 grams of water. So if I have a 6% volume to volume, that's going to equal a 4.7% mass to mass. Just a little interesting sidelight. Now, there are certain things that it doesn't make sense to use a percentage. Does it make real sense to use something like 0.0000001 0.01%. Does that make sense to you?
No.
No.
So what we do is we incorporate different terms. One of those is parts per million. And if you get to a sample that's small enough, you can even go parts per billion. Now you can turn, remember, percent is per 100. Cent means like century. It's per 100. So you can turn a percent into a parts per million by just simply taking a ratio. If you have 1 part per 100, that's equal to X parts per 1 million. If you solve that out, you will get 1 million divided by 100, or X is equal to 10,000. So literally speaking, in order to take a percent to a parts per million, all you have to do is multiply by 10,000. Because what you're really doing is you're multiplying 10,000 over 10,000 times your percentage over 100. So if I have a 50%, solution, if I want to know how many parts per million, I multiply 50 over 100 because that's what a percent is. Then what I do is I multiply that by 10,000 over 10,000. That 100 by 10,000 equals a million. The parts times 10,000 equals the parts per million that we're going to get. Make sense, guys? Am I talking crazy? I like talking crazy. Are we good?
Yep.
Do you need me to turn some percentages into parts per million?
Yes, please.
Okay. Give me a percentage. You wanted the question, Rebecca. Give me a percentage.
65%.
Okay. You sure don't want to ask me something harder? Okay, I need a new slide. There we go. I haven't put in the comma in there. Easy peasy, Rebecca. Okay, Rebecca? Going backwards. I'm sorry, what?
It. Yeah, I kind of get it. Why'd you divide it twice?
Why did I?
Like 100 and...
Why did I divide it by 10,000 over 10,000? I'm sorry, ask the question, Rebecca.
Yeah, I don't know. I'm just trying. So you divided 65 by 100.
That's what percent is.
Yeah, because of the percentage, and you multiplied it by 10,000 over 10,000.
The reason I did 10,000 over 10,000 is 10,000 times 100, the denominator portion there, 10,000 times 100 will give me a million.
Oh, okay, and it's parts per million. Got it.
All right. Now, let's do something strange. This is kind of a number you'll see. Okay? Does that make sense?
Yes. Wait.
This is the kind of number you'll see when we're talking about parts per million.
Okay.
All right? If you want to get that to something like a percent, the way I would do it is I would take 45 divided by 1 million, because that's what a parts per million is. That's equal to what over 100. Okay? So in order to solve this, I'm going to take the 100 over to this side. I'm going to multiply both sides by 100, right, Rebecca?
Yeah.
So if I do that, I get 45 times 100 divided by 1 million
Mhm.
is equal to X. In effect, I've got 45 divided by 10,000.
Gotcha.
So that's how we go from parts per million to percentages. And I'm sorry, I can't figure this out. I believe it's going to be 0.00045. I don't want to trust myself on it. 0.0045. That doesn't quite seem right. It's right. But that's percentage. Remember, this is percentage. So 45 parts per million is equal to 0.0045%. Okay?
Mhm.
Now, the one I really, really, really want you to learn tonight is molarity. And what I really want you to understand is that when we call something like 6 molar, what this is really saying is that's 6 moles of your stuff in a liter of the solution. So the label for molarity, the label for the big M is moles per liter. That's going to help you when you start to try and figure out whether you have to multiply or divide these things out. And I had a student that came up with this brilliant idea. This brilliant idea was so beautiful, I stole it. Now, do you remember how we had the density triangle? If we have grams and volume, we divide the grams by the volume to get the density. If I have the volume and the density, I just multiply them to get the grams. You remember that? Guys?
Yes.
We can use the same thing here. Only this time we're going to put moles on the top and we're going to have molarity and liters in the denominator. So if I have moles and I have liters, I simply divide the moles by the liters and I will get the molarity. If I have the molarity and the liters, all I have to do is multiply the molarity by the liters. That will give me moles. If I have the moles and I have the molarity, I divide the moles by the molarity, I will get the volume. With that in mind, what is the molarity of a 100 milliliter solution containing 15.6 grams of sodium hydroxide? Remember, molarity is moles per liter. How are we going to get moles?
You divide the 15.6 by the molar mass.
I'm going to divide the 15.6 by 40.00 grams, which is the molar mass of sodium hydroxide. So Rebecca, can I get liters from this as well?
Yes. If you divide by 1,000.
Yep, if I
100.
divide by 1,000. Guys, you're going to get awful tired. You're going to do a lot of these problems, and you're going to get awful tired of showing that 100 times 1 liter over 1,000 milliliters. All you got to do is take wherever your decimal point is, move it to the right 3 places, and you have the number of liters. If you're given milliliters, move your decimal place 3 places to the left, you will have your liters. So if I have 62.5 milliliters, move it once, get from the 5 to the other side of the 5, move it twice, I get to the other side of the 6, move it another time, there's a 0 there. So 65.1 milliliters equals 0.0651 liters. I do that math out. I divide by the 40, I get 0.390 moles of sodium hydroxide. I divide that by 0.1. I end up with a concentration of 3.90 molar solution. We good, guys? Okay, somebody other than Rebecca asked, answer this. How many moles of HCl are contained in 250 milliliters of a 0.600 molar solution? Either think that a molar solution is moles per liter, or go back and use the triangle. How do I get moles if I have molarity and liters?
Take the milliliters and turn it into liters,
And then,
and then multiply by the moles over 1 liter.
just like that,
Yep.
there we go. Okay? These really aren't hard problems. Okay, but now they're going to get into hard problems. All right? Chemists are asked to make solutions all the time. And in order to make solutions, you're generally given how much you want to make and what the concentration you want to make is. So you got to figure out how many grams, because it's grams is the thing you got to weigh. So how many grams of iron 3 bromide would be required to make a 750 milliliter of a 1.75 molar solution? Okay, somebody other than Dylan and Rebecca. Where are we going to start with this problem?
Convert the milliliters to liters.
Okay, I have 0.7500 liters. Now what am I going to do, Cassidy?
Then are you looking for the molarity? Oh wait, sorry.
I'm wanting grams. So how do I get grams?
So you could convert the. Sorry, I've had a very long day.
No problem. You gave me the first part of the solution. That's enough. If you want to beg out, that's fine.
Yeah, I think I'm gonna back out of this
No
one.
problem. Before you go, Cassidy,
Yes.
you have volume and you have molarity, which is moles per liter.
Would you just multiply those
That's all you got
together
to do.
and
You're
then
smart.
just convert the moles to grams?
There you go.
Okay.
That's absolutely,
I was
it's not
really-
as hard.
Really thinking way too hard about that one.
Sometimes problems are as easy as you make them. So I'm going to take my 750, turn that into 0.7500 liters, multiply that by my 1.75 moles per liter. This gives me 1.31 moles. Now, if I add up 3 bromines and 1 iron, that gives me a mass of 295.6. All I got to do is multiply that by the 1.31 moles, and I got my grams. A chemistry student prepares a solution by dissolving 25 grams of sodium chloride in 250 milliliters. What is the molarity of the solution? Okay. Oh, I got 7 people here. You guys outdid the morning class by 3. Min, you there, Min?
Yeah, I'm here.
Good. Okay, Min. You want to know the molarity. Molarity is defined as moles per liter. If you dissolve 25.0 grams of sodium chloride in 250 milliliters, what is the molarity?
We find the molar number of mole NaCl first.
How are you going to do that? You're going to take the 25 grams and do what with it?
Uh, 25 divided by 58.5.
Absolutely. You're going to take that 25 grams, you're going to divide it by 58.5, which is the molecular weight of sodium chloride, and you're going to get the moles that way. Once you have the moles, Min, what are you going to do?
The mole divided by 0.25.
Well, if we're going to do sig figs, it's 0.2500, okay? But you got the idea. You got the general gist of how you're going to do it. Okay. Does anybody, do I need to go through these problems, or are they fairly simple for you? Are we good with these, or do I need to go through them? Tell me what you need, guys.
No, it's pretty simple.
Okay. Is everybody on base with Rebecca?
Yep.
That means
Yep.
I'm going to tag everybody, and all of you are going to be out except Rebecca. Baseball joke. Bad. Sorry. Okay. Yeah. What I did, if you want to, if you need to, these three problems show the three type problems that are generally encountered. You're going to go from grams to molarity, molarity to grams, or grams to volumes. These are generally the three types, and I go through step by step. So hopefully you're not going to have any problems. Now I got to ask you a question. Moles is found by getting, moles is found? You wouldn't know that I graduated with an English degree. Moles are found by taking grams, mass, and dividing it by molecular weight. Is the molecular weight affected by temperature? If I have iron at room temperature and I have iron at 1360 degrees, is the molar mass of iron any different? Come on, guys. There's no difference. How about grams? Are grams affected by
Yes.
temperature?
No,
Yeah. No.
No.
it's only volume.
Ah, volume is though, isn't it? Doesn't the density of water change as you change the temperature?
Yes.
Yep. Okay. We just got done saying grams don't change. So if grams don't change, what does change?
Volume. So
Volume does. So if I have changing temperature conditions, can I use molarity as a reliable concentration term?
No.
No.
Can't, because the concentration is changing because the volume is changing. So we had to develop a different concentration term. And yeah, there it is. And it's called molality. Molarity is designated with the big M. Molality is designated by a little m. And it is slightly different. Molality is moles of the solute over kilograms of the solvent. Remember, molarity was moles. Wish I just had one of those automatic things that I could just look at the screen and it would just move automatically. If you remember back to molarity, molarity was moles of solute divided by liters of solution. When we're doing molality, it is moles of solute divided by kilograms of solvent. The only thing I wanted to be able to establish this, because you are not going to use molality in this course. I just wanted to throw it out at you. So sometime when you're taking Chem 2 this will stick in your mind that there is another concentration term. You're not going to have to do any calculations with it. So we're going to basically forget those things. But what we are going to have to do is we are going to have to deal with dilutions. Rebecca, I got a solution there. You see my solution?
Yes.
I have an amount of solute in a given volume of liquid, okay?
Mhm.
If I add more water to that, if I add more water to it, have I added any more solute?
No.
So what is happening to my concentration?
It's getting less concentrated.
I add more water. Continue this thought.
No, it's less concentrated than that.
And a little more.
It's still less concentrated.
Still less concentrated. Now, let me ask you this, Rebecca.
Okay.
Are the moles of my initial solution equal to the moles of my final solution?
Yes, because you still have the same amount of solutes.
So my moles initial is equal to my moles final. So how do I get my moles initial? Don't I multiply my molarity times my volume? I multiply my molarity times my volume. That will give me my initial molarity times my initial volume will give me my initial number of moles.
Mhm.
But we just said the initial moles are equal to the final moles, which is also equal to my final concentration times my final volume. So I have this wonderful little formula down at the very bottom of the slide. Molarity final times molarity final times volume final is equal to molarity initial times volume initial. And the beautiful thing about this is you don't have to do any conversion of your volumes, because whatever I convert the final volume to, I got to convert the initial to, as long as the label of the volumes is the same. If I have milliliters here, right?
Mhm.
I'm going to have to multiply those milliliters by 1 liter over 1,000. But if I have it on the left side and I have milliliters on the right side, I'm going to have to do the same thing over here. Let's say I'm doing ounces. There's a conversion factor between ounces and liters. I'm going to have to do it on the left, and I'm going to have to do it on the right. As long as the label for the volume is the same left and right, then you don't have to worry about converting it. I always love things that keep me from doing hard work, which is why I avoid my wife. Okay. Okay, this is a strange thing. I have the slides out of order here somewhat. All right. What is the molarity of a solution that was originally 53 milliliters of 0.25 molar KCl that has been diluted to 100 milliliters? We're going to do it the long way first. I'm going to divide my 53 milliliters by 1,000, 1 liter over 1,000 to get the liters. I'm going to multiply that by 23 moles, and I'm going to get 1.3 times 10 to the minus 2 moles. We didn't add any more KCl, so this is the amount that we have in our final. So what I'm going to do is I'm going to take my 1.3 times 10 to the minus 2 moles, and I am going to multiply it by 1,000 milliliters over 100 milliliters, which is the same thing as saying dividing it by 0.1 liters. If I divide it by 0.1 liters, that means my new solution is 1.13 moles per liter. Now let's try and do it the new easy way. I got 150 milliliters of 0.350 molar sodium chloride. It was boiled down to 50 milliliters. What is my new concentration? I have my initial volume, my initial molarity, multiply those together. They're going to be equal to my new molarity times my new volume. 150 times 0.350 is equal to 50 times X. I do the math out. I get 1.05 molar solution. Now, this is a good time for you to be able to check your answers. I boiled the solution down. Are we expecting a more concentrated solution or a more dilute solution?
Concentrated.
So we started at 0.350. We ended up at 1.05. Indeed, the concentration is more concentrated. Are we okay with the dilution equation?
Yes.
Okay, we've been talking about getting moles though, haven't we? Cassidy, are the moles we're getting from multiplying a volume times a concentration, are those moles any different than the moles you get by taking grams of something and dividing it by its molecular weight?
No.
Not a bit of difference. There's nothing involved in it. So what I've done for you guys, all in of myself, it was at great expense. I've provided you with a third tool to do stoichiometry problems. And aren't we excited by that? Remember, stoichiometry, the first thing we do is we change our moles of known, what we're given of our known. We have to turn that into moles of our known. Then we use the molar ratio to turn our moles of known into moles of unknown. Then once we have our moles of unknown, we can use it to figure out what we need to define by that. Again, it's a three-step process. The only thing we have done is we have added concentration into the mix here. So what volume of 0.492 molar HBr will react completely with 25 milliliters of 0.540 molar potassium carbonate? Jackson, you around? I haven't bothered you yet tonight, Jackson. Are you off eating a sandwich, Jackson? Okay, Joe, I haven't bothered you either. You there, Joe?
Yeah, I'm here.
Okay, Joe, do you see the problem?
Yes, I do.
All right. Do you have a way to make either moles of potassium carbonate or moles of hydrobromic acid?
Potassium carbonate.
How are you going to do that?
I think it's 20. You turn the milliliters to liters, right?
Yep.
And then you divide it by no. Yeah. Yeah.
No.
Then it's either multiply or divide.
It's either multiply or divide. Okay, Joe. One easy way. Do you remember what I told you the label for molarity is?
I didn't catch that.
Okay, it's moles per liter. Okay. Now, if you've converted this to liters, what do you have to do? Are you going to multiply it by the 0.540 moles per liter, or are you going to divide by the 0.540 moles per liter.
Divide.
If you divide, Joe, you are then going to, dividing is the same as multiplying by the reciprocal, right? Right, Joe?
Yeah.
So if you divide by the 0.540, what you're going to end up doing is taking the 0.02500 liters, and you're going to multiply it by 1 liter over 0.540 moles. Is that what you want, Joe?
No, I don't.
So what are you going to do between the liters and the molarity?
You multiply it.
Going to multiply it. I'm going to take my 25 milliliters, turn that into liters, and multiply it by my 0.540 moles per liter. I do that. Oops, sorry, it's there on the bottom. I do that, I get 0.0135 moles of K2CO3. Now, Joe, what's the next step? I've got moles of one of my things. I want to turn it into moles of this thing. What do I have to do to turn moles of potassium carbonate into moles of hydrobromic acid?
Find the molar ratio.
Okay, what is it?
2
You're stalling,
to
aren't you?
1.
You're stalling, aren't you, Joe?
No, it's okay.
I used to do that all the time. Used to do that all the time on the stand. Anyway, you were absolutely right. If you have moles of potassium carbonate, you convert that into moles of HBr by multiplying 2 moles of HBr over 1 mole of potassium carbonate. So I'm going to take that over there. Now I have 0.0270 moles of hydrobromic acid. The question originally was, what volume of that molarity will react completely with that amount of K2CO3? So I have the molarity, 0.492, and I now have the moles of HBr. I have moles and molarity. What am I going to do, Joe?
Now you want to divide.
Now you want to divide, yes. You're going to take
Moles
your
divided by, yeah.
You're going to take your 0.0270 divided by the concentration, and you're going to get 0.0549 liters. Questions about this, guys? The moles we are getting from concentration and volume are just the same as the moles that you got by dividing grams by molecular weight. You can solve stoichiometric problems in the same manner. What mass of sodium bromide will react completely with 37.09 milliliters of a 0.825 molar lead 2 phosphate? Joe, done a great job. Great job. I got to see who else I got to bother. Jackson, you out there, Jackson? Okay. Who thinks Jackson went out to the local bar and just left the Zoom on? It's either that or he can't talk to me. Dylan, you're out there, Dylan.
Yep.
Do I have a way of getting moles of one of my 2 things?
Yes.
What is that way?
The PB3PO42, you would take that and turn it into liters and then multiply by the molarity.
And that will give me moles of lead 2 phosphate. Then what am I going to do, Dylan?
You're going to take the mole ratio.
I'm going to take the mole ratio to get moles of sodium bromide. At this point, it just becomes a normal stoichiometric problem. I turned the milliliters into liters, multiplied that by my concentration, ended up with 0.0306 moles of lead 2 phosphate. Multiplied that by 6 over 1. This gives me 0.184 moles of sodium bromide. Now all I got to do is figure out that there's 102.9 grams of sodium bromide for every 1 mole of sodium bromide. Questions, guys? Does anybody have any questions? Seem fairly straightforward, guys?
Yeah.
Fairly straightforward? Okay. We'll complicate it just a little bit. I have 13.11 milliliters of a 0.250 molar barium chloride. That's going to react with 19.80 milliliters of a 0.225 molar silver nitrate. What mass of silver chloride will be formed? Blake, do I have a way of getting moles of barium chloride?
Yes.
Do I have a way of getting moles of silver nitrate?
Yes.
What kind of problem is this?
Would it be a ratio problem?
Nope.
No. Oh, you mean like divide or multiply?
Nope.
Oh man, I'm losing you. Stoichiometric problem?
It's going to be stoichiometric, but it's a special kind of stoichiometric. If I gave you grams of barium chloride and grams of silver nitrate, remember there was a special stoichiometric type problem.
Is it the one with the 4 steps, like the grams to grams?
No.
Man, I'm shooting in the dark here.
And you shot yourself in the foot too. Anybody help him?
Limiting reagent.
Limiting reagent problem. Okay, Blake, that's how you recognize. Blake, you out there?
Yeah, gotcha. That makes sense now.
You recognize a limiting reagent by the ability of both of your reactants. You have the ability to make moles out of both of your reactants. So like that, like a limiting reagent problem, we're going to solve it the same way. The only difference is the way we're getting moles to begin with. So I'm going to multiply my liters by molarity of my barium chloride to get moles. I'm going to multiply my liters times molarity of my silver nitrate to get moles. Next step, I'm going to figure out that there is a 1-to-2 ratio for barium chloride and a 1-to-1 relationship between silver nitrate and AgCl. So I form from the barium chloride, I took my 0.00328, multiplied that by 2/1, and got 0.005656. I took my 0.00446 moles of silver nitrate, multiplied it by 101 and got 1-to-1 and got a 0.00446 moles of silver chloride. Blake, which one's limiting?
The limiting is going to be the silver nitrate.
Okay.
Yeah.
So I believe the question asked for just for the grams of silver chloride. I've got moles of silver chloride. What do I do to finish it, Blake?
You got moles of sodium chloride. Would you just multiply the moles by? Wait, we don't have Ag. Yeah, I'm not sure actually.
Okay, if we have moles of something, how do we get grams from it?
Oh, you just multiply it by its molecular weight.
Don't you wish you had me prompting you during the test?
I do.
Okay. Guys, this is the last problem. It's not going to make sense for me to start acids and bases right now, and this is kind of where we ended for my morning session. So I'm just going to let you go early, okay? But I'm going to have you, I want you to answer this question. I'm going to go away for about 5 minutes or so and come back and we'll talk about it. What you want is you want the volume of 0.984 molar phosphoric acid that will react with an amount of grams of calcium hydroxide. Which one can you get moles out of?
The calcium hydroxide.
You can get moles out of the calcium hydroxide. Then, once you get the moles of the calcium hydroxide, can you get moles of phosphoric acid?
Yes.
Once you get moles of phosphoric acid, you have the concentration of your phosphoric acid. Can you get the volume?
Yes.
Work on it. I'll be back in about 5 minutes, okay? Okay, guys, we have an answer? Or have you all buggered out on me? Well, it says that there are still 8 of you in there. Anybody have an answer for me? Anybody have an answer for me? Anybody out there? Anybody out there? Anybody out there?
Yeah, I was just still working on
Oh,
it.
sorry, Cassidy.
Oh, it's okay. I just wanted to respond.
I'm sitting here screaming. Nobody's answering. So I got 8 people I think have gone out to dinner.
Well, I messed up on the molar weight of CaOH2.
Yeah, so did I. So when you just type that in there,
Oh, I did too.
was it actually I think 74.1
That sounds better.
is what I got.
Okay, cool.
32 plus 40 plus 2. You got 74 point what?
0.1.
Okay.
hmm
If you can take it out to one, is it 10?
It's 0.92, so
One.
0.9.
So it would be, this is better. That's
You
more
got it.
better.
Mhm.
Okay, 0.14.
I have a question, Professor.
Yep, I'm here.
What's that dollar sign represent
What dollar sign?
by the PO4?
Uh,
Second equation.
if you look above a 4,
No, I was just kidding. I was
thank
messing
you. Okay. So you can see professors can screw up just as easily as you can. I got 99.6. Is that better for you guys?
I think
that
you
more better?
switch the 8s around.
Twitch the 8s around.
It says 0.0980 and then 0.0908.
Ah,
I don't know if that makes a difference. Probably doesn't, but oh yeah.
I think the answer is correct. I just transposed them in the slide. My calculator was right. Okay, guys, that's all I have for you tonight. I mean, I could have gotten into acid bases, but we'll just leave that for another time. Now, we're going to get into acid bases on Tuesday. That's also when we're going to start to get new material, guys. This is, up to this point, this has all been review. We're going to get into the kinetic molecular theory of gases. It's hard to understand. And if you got friends that have been not coming because of the fact that this has all been review, well, tell them now's the time that we're starting to do new stuff, okay? Anyway, that's all I got for you. I still have Joseph here. I have Blake and Cassidy. Do I have anybody else? Dylan, you're still here? You never answered me though, Dylan.
I was doing it still, and then we changed the answers, and I got confused.
Okay,
Yeah,
are you okay now?
Go ahead. You go.
Yeah.
Dylan, you're okay?
Yep.
Joseph, are you okay now?
Yeah. The only reason I didn't answer is because I was like, my fingers are greasy and I was eating some food, so.
No problem. Don't worry. I'm just pulling your chain. Okay, guys, that's all I got. So I will see you again on Tuesday, okay?
Cool.
All right. See ya.
Take care.
Thank you.
Is Rebecca still here? Arthur, I'm going to get you next time for sure. Take care, man.